before we get started. I'm making sure to record this video, so that later on, if you want to rewatch me go through all of the notes or a portion of the notes, or if your internet goes out partway through this lecture, go back and see the notes, you will be able to do that. So if you see, I recorded our last week's notes and posted them up, like I said, right under the class recordings tab. So every single one of these will be the date that we had that specific class on, and then sort of the name of the subject that we covered. So that you can go back and rewatch me go through all or part of the notes if you need kind of a little bit of a refresher on some of the stuff that you're talking about. And it might be especially useful for the end of the notes today, because we're going to start to get into something that a lot of people find a little bit tricky at first, but I've heard from them going back and rewatching and going through it a couple times helped them out a lot in kind of understanding what was going on. So before we go ahead and jump into our first round of notes here this evening, does anybody have any questions, concerns, comments from the first week? Any policies that you're still not a little bit sure about, or any online or virtual class stuff that you still need a little help understanding?
I'm fine.
All right, good to know. Thanks, Andrea. Where are we at? There we are. Okay. All right, so today we're going to talk about kind of three major topics: states of matter, phase changes, and heating curves. And if you don't know what any of those are right now, don't worry about it. We'll talk all about it over the course of this evening. And like I said, a lot of these things, especially the states of matter and phase changes, you probably have already heard of some of them before or understand a little bit about what they are without even realizing some of the science that goes on behind it. So when we're talking about states of matter, what we mean by that is things like solids versus liquids versus gases. So the different states that matter can be in. So matter, if you haven't heard that term used before, is sort of a general science term that means stuff. So everything in the universe is made out of matter. All of the gases out in the galaxies, and the material being burned up in our sun, and the plants and animals, and magma and rocks and crust that makes up the earth, it is all matter. Matter is just kind of the general science word for things or stuff. So one of the interesting things that scientists discovered about matter when they started observing it down at the microscopic level is they find out that matter isn't just sitting there doing nothing. It's made up of thousands or millions or billions of these tiny, constantly moving particles, these tiny little individual pieces or molecules. So this idea that these tiny particles that are moving around all over the place make up all matter came to be known as the kinetic molecular theory. So kinetic essentially is a science word meaning motion or movement or moving things. And then molecular for teeny tiny microscopic particles, and then theory being a scientific theory. So the kinetic molecular theory is the theory of tiny particles that move around. So all the matter in the universe, everything in the universe is made up of these tiny particles. Something else that scientists figured out about these particles is that as the temperature of the matter increases, the motion, the movement of the particles increases. So as you make the matter hotter, the particles start to move faster and faster and faster. So we call that motion kinetic energy. So we'll come back to talking about kinetic energy kind of as we're going through some of our different states of matter here. And so as you increase the temperature, the particles move faster. The kinetic energy of the matter goes up because of all of that motion. So we have these tiny particles. They make up all the matter in the universe, and they move around faster as they get hotter. So there's sort of three different configurations or three different states that we can normally find these particles in. These particles can make up solids, liquids, or gases. There's actually a fourth one. It's called plasma. It's kind of confusing, and we're not really going to go into it in this class, so don't worry about that one. Focus on the big three: solid, liquid, gas. So solids are matter that have the lowest amount of energy. So this Ke right here, this stands for kinetic energy. And solids have the lowest energy amount. So the particles of a solid can kind of vibrate next to each other, but they can't really move around each other. They're pretty stuck in place. So if you look at like your computer or your phone or the table that you're sitting at, those are all solids. And as you can see, they're not really doing a whole lot of moving around. They're pretty much set in place as they are. The other thing about solids is that they have what's called a definite shape and a definite volume. This means that their shape and their volume, the amount of space they take up, is going to be the same no matter where you put them, essentially, or no matter what you do with them. So like my computer mouse right here, this guy is a solid. And if I hold it in my hand, or if I set it down on my computer, or if I put it down on the table, or if I drop it on the floor, it's still going to be the same shape. It's still going to be this round computer mouse shape. That's because it is a solid. And if you're a solid, you have a set shape. This little block of particles in here is always going to be formed as a square block, no matter if they're in this glass vase or if you take them out and hold on to them or put them somewhere else. The shape of a solid remains the same. It does not change. Same thing for the volume of a solid. So volume, again, means how much space that something takes up. And solids have a set volume. Because their shape doesn't change, they always take up the same amount of space. Their volume is always the same. So if you're a solid, like a table or a computer mouse or a phone, you have low energy. Your particles don't really move around that much. You have a set definite shape and a set definite volume. You are set the way that you are. Your particles are set in place. They don't have much energy, so you're not going to do a whole lot of changing. What happens, though, if we take our solid and add some energy into it? Increase that kinetic energy a little bit. Well, what can happen is that we can change that solid into a liquid. So liquids have a higher kinetic energy than solids. Their particles can move around each other a lot more than a solid can, but they still stay relatively close together. Their particles aren't zooming around all over the place. They're staying kind of close, but they can move and swirl and whirl all around each other. That's what makes it a liquid. So definitely have some higher kinetic energy than a solid. Liquids do not have a definite shape. In science, we say that they have an indefinite shape. The shape of a liquid will change depending on what sort of container that you put it in. So for example, in my cup right now, you know that it's my cup because it has my name on it. There's some water in here, some liquid water. And right now it's probably filling up my cup to about here or so. And it's taking up the shape of the bottom of my cup. So it's a cylinder, it's round, it's about this tall. If I was to take my cup and pour it out on the ground, now the water does not stay in that same cylindrical shape. Now it'll flatten out and spread all over the ground that I poured on. Or if I put it in like a square Tupperware container, the water will fill up and fill in the sides of the square of the container. So there's not a set shape of a liquid. Water does not have a specific shape. Instead, it'll be whatever shape of the container that you put it in. However, while its shape can change, the amount of water cannot change. It's always going to be a set amount of liquid. So if I fill up a measuring cup from the sink and I have 1 cup of water, I can pour that 1 cup of water into my mug. Now my mug has a cup of water. I can pour this into a pan on the stove. Now that pan has a cup of water. The shape of the water might have changed from a measuring cup to a mug to a pan, but it's always going to be 1 cup of water. The volume, the amount of water, is going to be the same. It's going to be set. So that's what we mean when we say that liquids are an indefinite shape but a definite volume. The shape of the liquid can change around and move around because of all those particles that can move now that we have that higher energy. But a cup of water is a cup of water no matter where you put it. Speaking of water, hold on. All right. So now what happens if we take our liquid and we add even more energy into it? We really increase the energy of our liquid. What we can end up getting is a gas. So gases have the highest kinetic energy of the states of matter that we're going to talk about in this class. The particles in a gas can be completely separate from one another. They can move all throughout the container. So there's constantly gas particles that are zooming all around you that are filling up the room or the classroom or your car or your house, wherever you are. These gas particles are constantly moving at very high speeds all around you and all around each other. So the cool thing about gases is that gases do not have a set shape or a set volume. So a gas can change its shape and expand and contract in order to fit whatever container that you put it in. So if you put some gas into this vase down here, it's not just going to collect down on the bottom like the liquid did. It's going to expand and the particles are going to bounce all around and it's going to fill up the inside of that container. So not only does it not have a shape, but it also expands or contracts its volume to fit the container that it is in. So gases, nothing about them is set. They can get bigger, they can get smaller, they can take up this shape, they can take up that shape. The particles are so separate and they're moving so fast that these high energy gases can have whatever shape or volume is needed based on the container that they are in. So gas, lots of energy, no shape and no specific volume. It all depends on where you're keeping that gas. So to kind of put them all together, review a little bit, our lowest energy state of matter is our solids. So those particles are super tight and close together, not really moving. that has a set shape and a set volume. No matter where you put it, it's going to maintain its shape and it's going to be the same size. If you add in a whole bunch of energy, you can get liquids which have the kind of medium amount of energy. Liquids, the particles have a little bit more motion to them. They can move around each other. They do not have a set shape. Liquids kind of fill up whatever container that you put them in, but they do still have a set volume. A cup of water is a cup of water no matter where you put it. Finally, if you add in a whole bunch more energy, you end up with the gases, which are the highest energy state of matter that we're going to talk about. Lots of particle motion, very, very fast movement. Gases do not have a set shape or a set volume. They kind of move and expand and contract in order to fit whatever container that they need to go into. So solids, liquids, gases in terms of kind of energy level and particle movement. So like I said, a lot of these terms you've probably, at least the solids, liquids, and gases, you've probably heard of before without kind of realizing some of the more sciencey background that goes along with those. So does anybody have any questions about our solids, liquids, or gases so far? Anything about these three states that you want me to go back and talk about?
Gases, please.
All right.
I understood it pretty well.
Cool. All right. So if everybody feels pretty good with the solids, liquids, and gases, those are kind of our three individual states that our matter can be in. But in order to get from one to another, we have to go through some sort of change, right? We have to change our solid if we want it to turn into a liquid. And we have to change our liquid if we want it to go to a gas. So these changes in state are known as phase changes. So when we go from a solid to a liquid, or a liquid to a gas, or even a solid to a gas, that's called a phase change. We change the type of phase or state that our matter is in. We go from one type to another type. So I'm going to have you guys help me out with the first couple, because these might be things that you have heard of before. So say you have something solid, like say an ice cube. So you have a solid piece of ice. You leave it out on the counter for a couple hours and it turns into a puddle of liquid water. So we go from solid ice to liquid water. What is that process called? What happened to your ice cube? Melted. Precisely. So melting is when we go from a solid to a liquid. So water is a really great example, because melting water is something that a lot of people have experienced in their kind of daily lives. But anything that is solid can melt if you get it hot enough. So melting is when you take some sort of solid material and convert it into a liquid by heating it up to a specific temperature. What about if we go the other direction? Say you have some liquid water, you put it somewhere really, really cold, and then you pull out a solid chunk of ice. You've gone from liquid water to solid ice. What do we call that process?
Freezing.
Freezing. Bingo. You guys are good at this. Freezing is this exact process, but in reverse.
Mr. Michael, sorry, just want to
as
ask.
a liquid and go to solid. Yes, question.
Yeah, just I want to ask you about the lesson. Do we gonna have it like in the file, Or we have to take some notes?
So these, the slideshow that I'm going through with you guys right now is posted on the Google Classroom.
Okay, thank you.
No problem. So you can go back and look at these whenever you want.
Okay, thank you.
Good question. So yeah, freezing is when we take something that is liquid and we cool it down to a certain point and it becomes solid. So this is why we call that super cold part of your refrigerator a freezer, because that's what it does. It takes liquids, and usually liquid water, and makes it solid ice. So there's a specific temperature that melting and freezing happen at for each substance. And depending on the direction that you're going, you call it either the melting point or the freezing point. So, for example, water. All right. Oh, good to know, Leilani. Thanks for the heads up. Thanks for being here. So with water freezes and melts at 0 degrees Celsius. So if you take some frozen water, if you heat it up to just past 0 degrees Celsius, it'll start to melt into liquid water. So that is the melting point. On the flip side, if you take some liquid water and you put it somewhere slightly below 0 degrees Celsius, it'll start to freeze. Hey, Jessica, no worries. Thanks for being here. So you take that water below 0 degrees Celsius, it'll start to freeze into ice. So the temperature of 0 degrees Celsius for water is set. And if you take solid water and get it warmer than 0 Celsius, it'll start to melt into liquid. If you take liquid water and cool it down to 0 degrees Celsius, it'll start to freeze to solid. So that's what I mean if you ever hear anybody talk about the melting point of something or the freezing point of something. It's a temperature where we change between solid and liquid or liquid and solid. Some other ones that you might be familiar with include vaporization, which is also often called boiling. This is where you take a liquid and you heat it up to a relatively high temperature, and it starts to change into gas very quickly. So if you've ever put water on the stove and started heating it up in order to make rice or make pasta, it starts off as a liquid, and then as it reaches that boiling point, you see the little bubbles that start to come up and start to give off the top of the water. Those bubbles are gas water, known as water vapor. So those little gas water bubbles are coming up and going out into the air. And we call that vaporization or boiling. So it's a very fast process. We're rapidly changing all of that liquid into a gas. You can also have a much slower process where you change liquid to gas, and that is called evaporation. So think about like when there's a big storm and a lot of rainfall and stuff, and you go outside afterwards and there's like these huge puddles on the ground, either by the side of the road or on the sidewalk or something. There's these big puddles. You come back 24 hours or so later, and those puddles are gone. Now, obviously, the water in those puddles did not vaporize because hopefully, pray to God, it was not 212 degrees Fahrenheit outside, because that would be very bad news for everybody. Instead, they went through evaporation, which is where liquid particles slowly tend to change into gas particles. So it's a much slower process than vaporization, but it still is a way to change liquid to gas. It just kind of happens very slowly over time. Finally, in terms of liquid and gas, we can also take gas particles, cool them down, and change them into liquid, and we call that process condensation. So condensation, for example, is the reason that we get rain. So there's tons of water vapor gas high up in the atmosphere. Eventually, it'll encounter low temperature areas where it'll condense down into slightly larger particles. These tend to form clouds. So the clouds that you see in the sky are just water that's kind of clumping together and forming that cloud. Eventually, if enough water clumps together in the atmosphere and the temperature gets cool enough up there, those tiny little water vapor droplets will become big and big and big enough to where they start to become liquid droplets that then become too heavy to float on the air, and so they fall to the ground as rain. So that is where rain comes from gas in the atmosphere condensing into little liquid droplets that then fall out of the sky. So vaporization or evaporation will take us from a liquid form to a gas form, whereas condensation will take us from a gas back into a liquid. So those ones you're probably all a little bit familiar with in some way or another, especially melting, freezing, and boiling. But some that are a little bit more rare and you don't see as often in nature include when we skip over the liquid step entirely and go directly from a solid to a gas, or down from a gas to a solid. So if we go from a solid to a gas, we call that sublimation. It's where we take a very, very, very cold solid and heat it up extremely quickly so that it starts to immediately turn into a gas. So dry ice is a really good example of this. If anybody's ever seen dry ice at the grocery store before, or at like a party or something before, it comes in these big solid blocks right here that are extremely cold. These are actually blocks of carbon dioxide. So normally carbon dioxide is a gas in our atmosphere, but we figured out a way to cool down this gas extremely quickly and turn it into a solid. Then, when the solid becomes exposed to the air is very hot compared to these dry ice blocks. So sublimation happens, and you'll see this mist and smoke coming off of these blocks. It's not smoke like from a fire. Instead, it is this solid turning directly into a gas. So if we take a solid and heat it up really quickly so that it turns directly into a gas, we call that sublimation. And then on the flip side, if we take a gas and cool it down very, very quickly and very, very coldly down to a solid, we call that deposition. So these usually happen where we encounter big temperature changes that are so extreme, they cause the substance to skip the liquid phase entirely and either go directly from a solid to a gas in the case of sublimation, or directly from a gas to a solid in the case of deposition. So if we put it all together, we get kind of this little triangle chart that looks like this, where we have our three phases of matter: solid, liquid, and gas. And we have our little descriptions, or the names for the phase changes of when we go from one to the other. So for example, if we take our solid and turn it into a liquid, it's gone through the process of melting. If we then take that liquid and turn it into a gas, then it's gone through either boiling or vaporizing, or evaporation, depending on what type of temperature we're dealing with. If we cool down our gas and it starts to form liquid, that's called condensing or condensation. And then if we take our liquid and cool it down even further until it solidifies as a solid, that's when it goes through the process of freezing. Then finally, if we have our solid and heat it up extremely quickly and extremely hot, it'll go through sublimation to turn to a gas. And if we take our gas and cool it down extremely quickly until it goes directly into a solid, then it's gone through deposition. So kind of a handy little chart that illustrates all the ways and all the names for when we change from one type of state of matter to another one. And then remember from when we talked about our solids, liquids, and gases, as we go from a solid to a liquid to a gas, we are increasing the particle motion. So we're getting faster and faster and hotter particles. Whereas when we go from a gas down to a liquid and then to a solid, we are decreasing the particle motion. We're getting colder and slower particles. All right. Does anybody have any questions about our phase changes, our name of the different phase changes, what they mean, or between questions left over from our solids, liquids, and gases?
No, I understand everything clearly.
All right, thank you. Good to know. All right, does not look like anybody else has any questions at this time either. So we do have one more set of notes to look over for tonight. But before we get there, I wanted to point out a couple things. So this is where the notes for today live. So on your Google Classroom in the week 2 section, you should be able to find the January 12th Tuesday notes, states of matter. So that's where the notes that we just looked at are. And then for those of you who haven't seen it yet, the daily assignment for today is a pretty simple, straightforward kind of review of some of the stuff that we just talked about. So it has a little bit of kind of review of the different states of matter. And then there are 3 diagrams. And so the first part of this is to label the left diagram, the middle diagram, and the right diagram as a gas, a liquid, or a solid. So that's what kind of these first 3 questions are for. The next diagram has a review of the different phase changes that we talked about, like melting and deposition and all that fun stuff. And then we have a little diagram over here that hopefully looks a little bit similar to something that we were just looking at, hint, hint. And so we have 6 different labeled arrows on this diagram. There's arrow 1, arrow 2, arrow 3, arrow 4, arrow 5, and arrow 6. And so for each of these arrows, you're just going to label it with what type of phase change is it. Is it melting, freezing, deposition, sublimation, vaporizing, or condensing? So that's what goes in the final kind of 6 little answer slots down here. All right, and as somebody was asking in my last class, the form that I just showed you is the Google form version, which is what I know a lot of you like to use. However, you are also more than welcome to use the Google Doc version, if that is what you prefer. It's the exact same information and the exact same questions, just set up a little bit differently, kind of more in traditional worksheet type form. So in this one, you'd use these blanks to label if something is a liquid, a solid, or a gas. And then we have the exact same diagram down here. And so you just fill in the numbers with which phase change is being represented by that arrow. So again, if you like using the Google Forms, you're more than welcome to keep using that. If you prefer to fill things out on the Google Doc, you are free to do that as well. You don't have to do both of them. You can pick one or the other, whichever one works better for you. All right, any questions on the states of matter homework before we move on to our next section today?
I'm good for now. Thank you.
All right, good to know. Thanks, guys.
I'm fine.
Mr. Stanley, I'm gonna go back in and check it, but it was one of those where, and I think that was the one where I couldn't open up the reading doc, but the quiz I was able to open up.
Oh, okay. Oh, okay, yeah, right. Good to know. Okay, good to know. All right. So the next thing that we're going to talk about today is very closely related to those states of matter and phase changes that we were just talking about. And that is a type of graph known as a heating curve. So it has a couple different names that people use depending on their preference. Some people also call it a phase change diagram or a phase change curve. It all refers to the same type of graph. So I'll show you an example of a heating curve in just a second. And essentially, it's a way to show the temperature of a certain piece of matter as energy, usually in the form of heat, is added over time. So imagine sticking a thermometer into something and then putting that object on like a stove or a heating pan and reading that thermometer over time. Well, you might think that, oh, the temperature is just going to go in a straight line from cold to hot. It actually ends up looking a little bit different. And it looks something like this. So you see we have our temperature over here on the y-axis. And down here on the x-axis is our time. So as we go further to the right, that means more and more time has gone on. So like I said, you might think that it would be just a straight line, diagonal line from your starting temperature to your ending temperature. But instead, you get these two different kinds of lines, these two different kinds of phases. So you have areas where the temperature is increasing. So remember, as we go up on the graph, that means our temperature is going up. So you can see kind of 1, 2, and 3 areas where our temperature is going up. But then we also have these 1, 2 areas where the temperature is not going up. It's holding steady for several minutes at a time. So we're going to talk about what does it mean in these areas where the temperature is going up, and what does it mean in these areas where the temperature is not going up, where it's staying the same. So first up, we're going to rewind a little bit and remember when we were talking about kinetic energy. So remember, this is when we were talking about those tiny particles that are moving. And the faster they're moving, the hotter they are, and the more energy that they have. So the amount of kinetic energy that a substance has is related to how fast its little particles are moving. So this is when we were talking about how solids have a really low kinetic energy, Well, gases have a really high kinetic energy. And then again, as the temperature of matter increases, that also means that the particles move faster when they get hotter, which means that the kinetic energy goes up. So as the temperature gets hotter, the particles get faster. The kinetic energy goes up. So this is what's going on in those areas of the heating curve where the temperature is increasing. So we start off with a solid over here at our lowest amount of temperature and energy. So this specific heating curve is for water. So we start off, imagine that you take a big block of ice, you stick a thermometer into the block of ice, and you set it on the stove and turn on the gas. So it's going to start off as a big solid block of ice. And over time, the temperature of that ice is going to start going up. So that's kind of what this first area of the heating curve is showing us. We have a solid block of ice where the temperature is increasing. So the Ke over here means that the kinetic energy of our solid, the little particles, are going faster. So they might be still stuck together in a solid, but they're kind of vibrating faster and faster and faster. Eventually, this solid is going to hit the melting point, which for water is 0 degrees Celsius. And then it's going to change into a liquid. So eventually, once the solid is all changed into a liquid, the temperature is going to start going back up and up and up. So now this would be like we've taken that ice, we've melted it, and now that liquid water is sitting on the stove. And over time, that liquid, which started off very, very cold, is getting hotter and hotter and hotter and hotter. So that's kind of what's going on in this middle section of the heating curve. The temperature is going up. We're a liquid now, and so our liquid particles are moving faster and faster. Eventually, the temperature is going to go up, 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 and hit what is called the boiling point, which in the case of water, the boiling point is 100 degrees Celsius. So once that water hits 100 degrees Celsius, it's going to boil and eventually all get converted to gas, where once that happens, then the gas will start increasing in temperature as well. So the gas particles will get faster and faster. So these areas on the heating curve where the temperature is going up, where we have this kind of up diagonal of temperature, those indicate areas where we have a single state of matter that is getting hotter and hotter. Either we are a solid that is getting hotter and hotter, or we are a liquid that's getting hotter, or even at the very end over here, we have a gas that is getting hotter. So that's kind of the first three areas of the curve that I wanted to talk about. Solid getting hotter, liquid getting hotter, gas getting hotter. So that's three different areas. But what about these flat areas right here? What about these areas where no temperature is changing, where we're staying the same temperature over a long period of time? Well, in order to talk about those, we have to go over a different type of energy than kinetic energy, which is what we've been talking about so far with the particle motion. Instead, we need to talk about potential energy, sometimes referred to as PE. So whereas kinetic energy, Ke, was how fast the particles are moving around, potential energy, PE, represents how close together our particles are, how tightly they're stuck or fused together. The lower the PE, the closer together they are. The higher the PE, the farther apart that they are. So as you go from one phase to another, say, I don't know, from a solid to a liquid, or from a liquid to a gas, your particles are getting spread apart because they start super close together as a solid, and then they become further apart and around each other as a liquid, and then super spread far apart as a gas. So as you're going through those changes from solid to liquid and liquid to gas, our potential energy is increasing because they're getting more spaced apart. Because our potential energy is going up during this time, that means that our kinetic energy is not going up. So all of that heat that's coming up from our stove, instead of making the ice get hotter, now it's being used to turn the ice into a liquid water. Because we're not changing the kinetic energy, the temperature of our substance, our matter, stays the same. So this is why when we're changing from a solid to a liquid or a liquid to a gas, we have those flat areas on the heating curve. Because we're going through a phase change, so we're changing the potential energy, but we are not messing with the kinetic energy. So the particles are getting farther apart, but they are not getting faster. So because they're not getting faster, that means that the temperature isn't going to change. So that's what's going on in this flat part right here and this flat part right here. So this first one we talked about, we're going from a solid to a liquid, so we call that melting. So we start as a solid, and then over time, as our temperature stays at 0 degrees, we melt into a liquid. So we go from a solid to a liquid, so the potential energy goes up because we've got more spaced out particles. Then that liquid heats up for a while, and then we go through another phase change time, where now we're going from a liquid to a gas through boiling or vaporizing, whichever one you prefer. Again, we're really spreading apart those water particles, so our potential energy is going way up, but because of that, our temperature, our kinetic energy stays the same. So while we are melting or while we are boiling, the temperature is not changing. It's staying the same. And that's why we get these flat parts on our heating curve. All right, so if we put everything together, we can kind of follow our ice block on its journey from a big solid piece of ice to hot water vapor gas. So we start off at a pretty cold temperature with a big solid piece of ice. That ice then starts to heat up for a little while, so our temperature goes up. Once we hit 0 degrees Celsius, that ice starts to melt into a water. So our solid ice is changing into liquid water. Again, while we're melting, while we're going through that change, the temperature stays the same. The temperature is going to stay at 0 degrees Celsius until we melt the ice all the way until it is completely 100% liquid water. Once that happens, once we've changed everything to a liquid, now the temperature starts to go back up again. Our liquid is getting hotter and hotter and hotter until eventually our liquid hits the boiling point, which in the case of water is 100 degrees Celsius. So now our liquid is boiling or vaporizing. It's being converted from a liquid into a gas. So all the time while our liquid is boiling and converting into gas, the temperature stays at 100 degrees. It doesn't matter how long that your pot has been sitting on the stove boiling. If you put in a temperature probe as soon as it starts boiling versus 20 minutes later, it's still going to say 100 degrees. Eventually, all of that water will have boiled away and been converted into water vapor, which is a gas. And so now finally the water vapor will start to heat up as well, which kind of happens at the very end here. So we start as a solid, we get warmer, we then start to melt and turn into a liquid. While we're melting, we stay at the same temperature. Then once we're all liquid, we start to heat up and get hotter and hotter and hotter until we begin to boil. Once we're boiling and vaporizing, we're converting our liquid into a gas. But while that's going on, we still stay at the same temperature while we're boiling. And then finally, we've boiled all the liquid away. And so now the gas starts getting hotter and hotter as well. So any type of substance that you change from a solid to a liquid to a gas is going to have a similar heating curve as this one right here. The temperatures might be different from water, but it'll still have that initial heating period, the flat melting period, the second liquid heating period, the flat boiling period, and the final gas heating period. Again, while our temperature is heating up, we're staying in the same state, either a solid, liquid, or a gas. Whenever we're changing from one state into another, that is when our temperature does not change. It stays at either the melting point or at the boiling point until that phase change is complete. All right, so I know that there is a lot going on here with our heating curves. Does anybody have any questions about what's going on at the different parts of our heating curve here? All right, as always, this is probably one of the trickier things that we talk about here early on in the semester. I know a lot of people tend to get a little bit confused with it. So remember, you can always go back and watch the video of me going through it like I did just now, later on. Or please reach out, email me or text me if you think of any questions later on that come to mind right now. So before we finish up for today, I wanted to give you a little sneak preview of Wednesday's daily assignment, which will be posted early tomorrow morning. And that directly relates to the heating curve that we were just looking at. So we have a sort of generic heating curve right here. It looks a little bit different than the one we were just looking at, but it has all the same parts. An initial solid heating phase, and then a melting temperature staying the same phase, and then a liquid heating phase, and then a boiling phase, and then a gas heating phase. And it mentions in the instructions that this is ice and water that we were dealing with. So this is just the exact same as the heating curve that we were just looking at over here, just set up a little bit different with its proportions. So you notice that different points on this curve are labeled with these different letters, A, B, C, D, E, F. And so there's only a few questions on this assignment, and they all have to kind of relate to what's going on between the different letters. So it'll ask about from point A to point B, B to C. It'll ask about temperatures that's happening while this phase change or this heating is going on. It'll ask about states of matter that different portions of the heating curve are representing. And then some of them will say what's going on in this section right here. So if you feel pretty comfortable with the notes that we just went over and the heating curve that we were just talking about, then tomorrow's daily assignment should be pretty simple and straightforward. Again, though, if you get a little bit stuck on it or a little bit confused on it, feel free to reach out to me or rewatch this video, and I will do what I can to help you out. All right, let's see where we're going next. Here we are. So that pretty much wraps it up for the stuff that we're going over today. Does anybody have any final questions about the phase changes, the heating curves, the states of matter, anything that we talked about so far?
Yes, potential energy and what is K? Kinetic energy is how different? I don't understand that one.
So I'll go back to it. So the KE on this heating curve right here refers to kinetic energy. So kinetic energy is how fast are the particles in your matter moving. In the case of this curve right here, it's how fast are the water particles moving. So as the temperature goes up, the particles move faster and faster as they get hotter, which means the kinetic energy of our substance goes up. So essentially, it's showing that as the temperature is increasing, that also means that the kinetic energy of our substance is increasing. So like for this part right here, as our water gets warmer and warmer, the kinetic energy of our water particles gets higher and higher. The particles are moving faster and faster as they get hotter.
But why is the potential energy here in melting and boiling?
So the potential energy refers to how close the particles are to each other. So here, let me make this a little bigger. So when you melt, you go from a solid to a liquid, which means you go from the particles being very, very close and tight together in a solid to further apart and moving around each other in a liquid. So when you go from really close particles to further apart particles, your potential energy goes up because more higher potential energy means more space between the particles. Here, I think it's, here we go, yeah. So when you're melting or when you're boiling, you're going from one state to another. You're either going from solid to liquid or liquid to gas. And as you're changing between those states, you're getting particles that are further apart. So as the particles go further apart while you're melting, the potential energy goes up. As the particles get even further apart while you're boiling, the potential energy goes up. So the further apart the particles are, the higher the potential energy.
Okay, thank you.
Thank you.
No worries. So on these parts right here with the solid, the liquid, and the gas, the particles are getting faster, so the kinetic energy is going up, but they are not getting any further apart. They're staying the same distance. So the potential energy isn't really changing. On the flip side, when you're melting or you're boiling, the particles aren't getting any faster. Their speed isn't really increasing, but they are getting further separated apart from each other. So our potential energy on those parts is going up, but the kinetic energy isn't really changing. It's staying the same. Hence the temperature not really changing either. So same speed, but further apart. All right, good questions, really good questions. Anybody else have any heating curve or phase change or solid liquid gas related questions?